In this lesson, we'll discuss the basics of polarization, the polarization of light. And we know that light is an electromagnetic wave. An electromagnetic wave has, well, electric fields oscillating in space and interacting and producing, interacting with magnetic fields, which are oriented perpendicular to the electric field. And the whole propagation of these perpendicular waves is the direction of the wave itself, the electromagnetic wave, consisting of both of those types. All right, so that's light. Now, when we talk about the polarization of light, what we're talking about is the direction that the electric field is oriented. Whoops, this one. So in this graphic here, it's oriented side to side. In other words, horizontally, not vertically. Okay, and now we're going to just simplify that concept to just drawing lines like this. This shows the electric field orientation, and normally, normal unpolarized light has electric field components in all directions, and that's what this shows. Or sometimes just a single cross showing that the electric field is oriented 360 degrees. In other words, there's electric field energy in every direction. All right, so it's propagating through, and a polarizing filter will have an axis of polarization, which has to do with special molecules that basically chop off the electric field in a certain direction. So when it shows this like fence, these slats, it's showing the polarization direction. It's showing the direction that it allows the electric field through. So there it is. The electric field gets through, and the light has been polarized vertically. So, light has the property that it can be polarized, and that means it's given a particular orientation or vibration direction in a plane. And the material that limits the orientation to one plane is called the polarizer. Only lets the light pass through with the correct orientation, which is the orientation of the polarizing material. So, it's the direction of the vibration of the electric field. So, if we consider this vertically polarized light, so now we have actually vertically polarized light here. Okay, before it was unpolarized and it became vertically polarized. So if you have a vertical polarizer and you have the input being vertically polarized light, the polarizer says, well, thank you very much, I like you, I will let you pass. So the output is undiminished, unaltered. However, if we have a horizontal polarizer and we have that vertically polarized light, you can kind of think of this as, well, the vibration can't happen in this direction, you know, up and down with the sine wave. This blocks that vibrational mode, and so you have an output of zippo. It goes dark. In fact, if you have a polarized light in one direction, say horizontally, and put a vertical polarizer, you know, if you put the right angle orientation against that, horizontal and vertical, it prevents all light from passing through. So you literally get darkness. Isn't that special? Now, most light, like sunlight and regular light bulbs, is unpolarized. Generally, mostly at least, sunlight can be partially polarized, which means the electric field is vibrating in all directions. So there it is. And passes through a polarizer at this angle or any other angle. What passes through is the quantity of that light that's in that same direction. So this is the part that will pass through. And it's pretty much as simple as that. Okay, we'll get a little more quantitative now. And let's have the electric field polarized in this direction. So there's the light, the electric field orientation shown, theta degrees from the vertical, passes through a polarized filter that's vertical. Only the vertical part will pass through. So it's the vertical component. Well, how much of that is there? How much of E0 is vertical? It is the component that's vertical. So there it is. That's the part that passes through. And this is the part that does not pass through. It's the wrong orientation. So the adjacent side of a right triangle. So the amplitude is E0 cosine of theta. E0 cosine of theta. Makes sense? Now the intensity is proportional to the square of the amplitude, as we have learned. So if we square both sides, we get this. But by saying the amplitude of the electric field squared, that's a similar thing as saying the intensity. So the intensity is I0 cosine squared of theta. So that is how you determine the intensity of light passing through a polarizer whose angle of polarization is theta with respect to the original polarized light. Okay. So let's look at an example here. Unpolarized light going through a vertical polarizer, then through a second one rotated at 60 degrees down from the vertical. What's the orientation intensity of the transmitted light? Okay, so the unpolarized light passing through a vertical polarizer will chop off all of the horizontal polarized light. But realize the polarization is in every direction, and even at angles other than perfectly horizontal, the vertical component of those will still pass through. So I wonder how much of the quantity of light passes through. If you put one perpendicular to this, it chops it all off. So how much do you think this chops off? If you think of every particular orientation of the electric field, and it's all of them in there, you let all the vertical parts through, you get, with the intensity starting out with I0, you get the vertical part through, but that's the vertical part of all of it. So this initial thing is simplified. I1 will just be a half of what the original was. So it cuts half of it off. All the horizontal, all the verticals left, that's half. Make sense? All right, now it goes through and only allows of that vertical polarized light, and only allows the 60-degree part of that through. Well, remember, the orientation is in every direction, and the vertical component here that gets through, part of that vertical is in this direction, okay? And that's what we're showing being passed through here. So I2 is I1 times the square of the cosine of 60 degrees. That's 1/4. So it's I1 over 4. So I, the intensity that gets through, is 1/8 of the original. 1/8 and oriented at 60 degrees to the vertical. So it's funny, what we actually did here is we took unpolarized, polarized it vertical, and then we actually twisted the orientation of the polarization. It went from vertical and we twisted it. Okay, you can't put a horizontal polarizer here, but you can actually rotate the orientation of the electric field in this manner. So now what's the big deal about polarized sunglasses? Why are they effective and what do they do? Well, if you have unpolarized light, it strikes an angle at the surface at an angle. The reflected light is polarized in the plane of the surface. So here's a nice graphic showing that. We have unpolarized light coming in. This could be a surface like water. Typically water has glare to it. And the glare is really the reflected part of the light off the water. But what happens is, for the most part at least, the vertical part of the electric field refracts through, but that can't reflect. The vertical part is essentially chopped off, at least most of it is. There actually is a special angle where all of it is. But in any case, you can visualize only the horizontal polarization. The direction of the plane itself is what bounces off. And that's what we're seeing. We're not seeing this. So that's what a surface like water does to light. So polarized sunglasses are going to be made with a polarizing material that eliminates this reflection. You don't want to see the reflection. So if you put a vertical polarizer in there, it will reduce the glare. The vertical polarizer will chop off this And basically then you don't see the glare of the water. And look at that marvelous relaxed view compared to the glare that otherwise would be there.